Thank you. Can I? Sorry?
Does everybody know you?
I don't know. So, hello. I'm.
Can you introduce yourself?
As you want. Okay. So I'm Emmanuel Zambrini. I used to work. I did my PhD at the Group of Applied Physics in Geneva, and I'm doing a postdoc just started last month with Stefano at the Laboratoire d'Information Quantique here. So today I'd like to present work that I did in Geneva recently, in the last few months. It's entitled Informationally Restricted Quantum Correlations, and it's about prepare and measure scenarios which are related to communication complexity problems, and we're going to try to look at ways or see how we can limit the amount of information that is communicated in such scenarios. So a prepare and measure scenario, let me first define what it is. So you have two parties, Alice and Bob as usual, and Alice holds a random variable big X, and she will receive some input, small x, which is sampled from a probability distribution, which I call Px of x, the probability distribution of this random variable. Depending on her input, on the input that she receives, she will send a different quantum state to Bob. So this set of probabilities and states defines an ensemble in quantum mechanics. And basically this ensemble is the message, the quantum message that Alice is conveying to Bob. Then Bob has some measurement choices, so let's give them a finite number of choices. Let's say Alice has n inputs, n measurements. Bob has L settings, and then Bob has k outcomes. Okay. So you can have a quantum message, but of course you could also have a classical message, and we are also going to look at those cases. So we could instead have just some m, which is a function of x. Okay. And so such a scenario or an experiment which is realized in this way will be characterized by a probability distribution PB of xy. And now in these sort of scenarios, you can play different kind of games. For example, you could look at the type of games where Bob tries to guess the input of Alice. Okay. So in that situation, you would be looking at the probability of having B equals x. Okay. And so let's think about this classically first. So classically, we have our message M, write it here. So you could, let's say, you could in the message encode the full information about x, okay? So you could say that M is equal to x, in which case the information that is conveyed about, so the information which is conveyed in the message holds log n bits. So I'll write I of x, information about x, is equals to log of n. All right? So such a message has information ix that I wrote there. Okay. And then you could also imagine another trivial case, which is, for example, the message is always the same value. So in this case, you don't transmit any information about x, and then you have zero information. Okay, so these are the trivial cases, and we'll be interested in looking at the non-trivial case where you have a message. So classically, the message would have dimension b, strictly smaller than the number of preparations. These are the interesting cases. Okay. So now we want to think about this in a quantum world. So in the quantum case, the first question that might come to mind is, how do we limit the amount of information in the message? Because in the classical case, it looks quite trivial. Basically, the amount of information is directly related to the amount of labels that you have in your message. Okay? But in the quantum case, how would you do it? So one thing that you could think would be that you could restrict the Hilbert space dimension of the states that you're sending. Okay? So if you restrict the Hilbert space dimension, you're doing some kind of analogous thing to restricting the number of labels. So as you might have guessed, I will try to argue and show you that this is not the best way to do it, and that there is a better way to do this, basically. So why is dimension? What are maybe the indications that the dimension might not be a good way to limit information? So first of all, the dimension, is discrete. This means that when you limit the dimension, you're actually limiting discrete amounts of information. So you're not able to limit information in a continuous way. You can only do it for a discrete amount of information. And ideally, we would, of course, like to bound it continuously. The second thing is that you could have a qubit with big D with less than a dit of information, with big D strictly bigger than small d. Okay, so what do I mean by this small example? You could imagine that you have a Q quart, which is mixed with noise. Okay, you just shrink the block vectors, and you get something which has 1 bit, or even you could go to 0, or very close to 0. So if you limit the dimension to 2, for example, here, if you want to say that you're limiting the information to 1 bit, if you limit it to a qubit, you're missing out on all the cases where you have higher dimensional systems, which only have 1 bit of information. So the point here is that we might be losing something. If we bound the dimension, because there's this whole other, yeah.
Actually, I'm a little bit confused as to what we are losing and what we are trying to gain, actually, here.
Okay. Okay, so.
What is the question that you're trying to?
All right.
What are we doing?
Yes, so basically, in this sort of scenarios, where you send either a classical or quantum message, I want to know how we can limit the amount of information in the message. And the usual approach, which is found on the literature, is that when you go to the quantum case, so classically everything is quite trivial. But when you go to the quantum...
What is like the answer? You can have
classically...
preparations or do you like...
So classically, the answer is to limit the amount of labels in the message. So that directly limits the amount of information that you can send.
Is this the only way? Or
no.
The quantum case was like the classical case. You could have many labels and not choose them optimally. You could have a quality distribution of the labels with some noise. So all this would be also true for classical case.
But so labels. But isn't that kind of what we're trying to do when we bound the dimension?
Yeah. So I mean, what you said was
yes.
The quantum case also applies to the classical case.
Yeah, but. Sure.
So you want to limit the amount of information by...
Yes. True.
Like constraints on the type of... so the channel is ideal.
Mm-hmm.
It's ideal channel, right? So against channel, there is no noise.
There's no noise.
But
Yeah.
the preparation could be different types of encoding, which could be noisy encoding, or like I prepare mixed states, even classical, like...
Exactly, yeah.
That, right? So is this not a way to limit information or not?
So the question is if limiting the labels is a way to limit information.
No, that I understand, but limiting what are you saying these are the only ways to limit information in the classical case, or?
No.
Okay.
No, I'm saying that this is usually done for prepare and measure scenarios. For example, for dimension width. In the literature. Yeah.
If you want to measure the communication abilities of some source, it's entropy. So
yes.
It's a natural thing that people do in information theory, not the dimension, the number of levels.
Yes, but at least in the dimension witnesses and all the literature on dimension bounds, this is normally how they look at the classical case.
It's the way some sub-fraction of the community consider this problem.
Sure. But, there are other ways, indeed. So okay. So let's say I'm focusing on limiting information in the quantum case. Okay. And
asking in what ways could there be a limit to the information that's transmitted?
Yes. So what approaches could we use? Well, basically, I'm saying that in the literature, this approach has been used a lot. Okay. This is, for example, all these articles on the dimension witnesses. Okay. And prepare and measure scenarios related to semi-device independent applications. All right, they all use this dimension bound, or a lot of papers use this dimension bound to limit communication. All right, and I want to argue that in quantum.
It sounds as if the purpose is to limit communication, whereas kind of I see the other way. I mean, you realize that a dimension bound is a limit that you can use to put a bound to the dimension.
Yes.
Here you're asking, are there other things that also...
I'm asking if this is enough
for?
To limit communication. So basically, if the idea is to limit the amount of information that you're sending in the message, I'm asking whether limiting the dimension of the Hilbert space is enough to capture all the physics. The idea is limiting communication, right? You want to limit the...
It also depends on what you're doing now. If the thing is that you're doing a special device, you can only manipulate, let's say, the polarization, the grid of the photon, then you're limited to the cubic space. So it's natural because it's a cubic. Right?
If you know it's a single photon.
If in your experiment...
It's not just...
If in your experiment you know that you're working with qubits, that's what you're saying? Okay, so but that's also a point that I think was kind of, at least was a motivation for us at the start, is that, well, D is a theoretical object. It's an artifact of the theory, so you cannot, I mean, it's very hard to justify in an experiment that you actually have a D-dimensional system. So this is an argument to why maybe this is not the best approach. This was my third point. Okay, are there maybe more questions? Because maybe this is not clear yet exactly what I'm trying to do. So is it, probably not everyone here is familiar with semi-device independent protocols, but so in these protocols, they limit the dimension, and I want to see whether this is sufficient to capture all the quantum cases with information restriction on the message. Okay, so I'm asking the question, let's say I'm asking the question without referring to any previous work, whether if I want to limit the amount of information in the message, I can do it simply by bounding the dimension, or if I have to do something else, something more.
That if you bound the dimension that the information is going to be bounded?
So sorry, if you bound the dimension, yes?
You're
then
asking if you want to bound the information, what are the constraints?
So you're asking whether it's clear that if you limit the dimension, you limit the information in the message. Yes. So that is a necessary condition. I wonder now whether it is sufficient. Okay. So, for example, this point is, I think, one of the strongest ones is that you could have, for example, a Q quart, which only holds 1 bit of information, a Q quart ensemble with just 1 bit, okay? And if you limit the dimension, then you don't look at these cases. Now, whether you can have an advantage by using a Q quart mixed with noise in a given scenario with respect to using a qubit, this is another question, okay? I'm just saying, maybe there is, maybe some scenario or some game exists where this is the case.
So what you are saying is that it may be too loose to bound the dimension?
Exactly, yeah. It's not enough to, for this purpose of limiting information.
So why don't you want to bound the quantity which measures the information, which is channel information?
Yes, so okay. We did it in our way because it hadn't been done in this framework. So people were using the dimension bound, and so one of the main things that people saw, for example, I will come back to this later, close to the conclusion, but you have two sorts of scenarios. So this is an example where the dimension bound has caused problems in the literature. So you have quantum communication protocols where you send, Alice sends some quantum state to Bob, and you have another type of communication protocol which are called entanglement assisted classical communication, where Alice and Bob have access to pre-shared entanglement, and then Alice can convey a classical message to Bob, okay? And if you use the dimension bound, and several authors were puzzled by this, we have a long list of articles mentioning this, is that with the dimension bound, sometimes you found that this kind of scenario was more general, so meaning that everything you can do here for specific kinds of games, you could do in this scenario. And sometimes people found the reverse thing. So there wasn't a clear relationship between this and this.
The entanglement assisted classical communication scenario, which dimension are you binding? The dimension of the shared entanglement? The system which shares the entanglement, or is it the classical bits? What are you binding?
So yes, so they bounded the dimension of the shared entanglement and of the message. Yeah. Well, the message is classical here. And here the dimension would be bounded in the quantum message. Yeah. So there was this kind of puzzling thing where people weren't quite sure what to make of it because they were using the dimension bound, for example, in these kind of scenarios. Okay. So is there any other question about this first part? It will become more clear exactly what we're doing. It's just maybe if you're not familiar with these papers which use the dimension bound, then maybe it's not completely clear yet why we're doing this. So what we're going to do is trying to limit information, which I call IX, and I will define it. And we do it, we write IX as a function of the conditional mean entropy, which we note H of X knowing the ensemble. So, okay, this might be a bit of a loose notation for people used to working with mean entropies. What I mean here is that this is the uncertainty about the random variable X knowing that you've received the message epsilon, okay? So I will define all this. Okay. Okay, so again, we're looking at this kind of scenario, and now I want to write this uncertainty about X knowing the message. And this is actually related to a quantity which many of you might be familiar with, which is the guessing probability. Sorry, guessing probability of X knowing the ensemble epsilon. Okay, and the guessing probability we compute it by maximizing. So, okay, I'll write it down. We do a maximization over Bob's measurements here. So Bob's decoding function of sum over X with the distribution Okay, like this. And just an important thing is that these measurements need not be contained in the original scenario itself. Okay, we do an optimization over all possible measurements, meaning that we look at kind of the equivalence, an alternate scenario where you only have one measurement on Bob's side, but you actually look at all possible measurements. So this is optimization over all possible measurements. Doesn't mean that in your scenario, when you're studying a particular scenario, you have the possibility of using this measurement. Okay? This is just to define the maximum information cost. Okay. So then...
So it's the guess probability average over all possible x's, right? So you take all possible x's,
yes.
each of them you look at what's the probability that Bob says x.
Exactly. So here it would be n of b equals x. So basically, your output would be equal to x. Yeah. Okay. So then we define.
So n of x. So n depends on x. Is that right? This is what I see.
Well, yeah. The p of m. Yes. Then the output is equal to the input of Alice. Yes. Okay. So then the information about that, yes?
Computation is very strange, no? Because you solve for x, so it will be the mean entropy of x, but of the quantum systems percent, given x. I mean, but this that would be the most other way to write it.
You'd reverse it?
No, it's the mean entropy of the quantum systems. No, it's
yes.
Average probability.
And say condition on x in the sense that you.
I think the notation is. I already got this comment actually from Thomas, and I think it's a very good one. Yeah. Sorry. Yeah.
I don't see the problem.
Well,
as a definition,
but
makes sense. I don't know what you do with it.
Yeah. Okay. But maybe with respect to how people write normally.
The mean of a classical variable
yes.
would be minus log of the biggest, but not average over. Okay, maybe
okay.
The biggest will be the maximum probability, and then if this variable is correlated to another one, then you define the mean entropy of that variable condition to the other one as the average of the guessing probability of the conditional distributions. So this is why it seems to be strange.
All right.
Actually, the sum over x, px, x should also be replaced by the maximum. Yeah. So you should maximize over all possible input x.
Yeah. Okay. This is an average.
Possible measurement. So nx, and you would take the one.
Okay. So we do an average over x. It's a version of the guessing probability. You could also, for example, consider.
But then it's not HP.
See, here x is a classical variable. That has nothing to do with the channel on the A to B. It's a variable
yes.
known, which is a given probability distribution.
Yes.
It's not the entropy of that variable in scenario. So writing it as the entropy of that variable seems strange.
I agree, and also since I discussed with Thomas, he also had the same comment, and this is just how we noted it at first, but none of us had worked previously with conditional mean entropies, so that's how we wrote it. And I think it holds, it's just the notation that is not clear, but maybe you can tell me more about it later. So I'll define this information as the uncertainty on the random variable x minus the uncertainty the conditional mean entropy. Yes, so now I'll define it where this h mean of x is minus log of the maximum over x of p x x. So if you take a homogeneous distribution, then you have, this is log of d.
That's the real definition. Exactly. Yeah, right. So that's the normal.
Okay, but this is not the conditional one.
No, but even the conditional one would be what you wrote.
But so this is correct for a non-conditional, the normal mean
The
entropy.
question is not about conditioning.
About the classic.
But
Yeah.
It's about the variable, which is the quantity, the main quantity in the entropy. It's not X in the second one. It's something else. It's a quantum system of information.
Yes.
Which is
Correct. Yes.
with
Yes. And but
So here
yes. So,
if we want to maximize over x, so then you should also maximize over x, and in the other expression, if you want this to be a mean entropy. It's just a quantity which is not a mean entropy, but it's maybe interesting.
okay. So your point is that we should not that averaging the guessing probability here is probably not correct.
If you want to define I think I agree with you. If you want to define a conditional mean entropy, look at what is the maximum guessing probability by maximizing over all possible x, and also maximizing over all possible POVM on both sides.
And it's always this is trivial one, because you're always just you maximize over x. For one x, you're always going to be giving the right answer. I mean, you need somehow to take the different possible x's into account. Otherwise, but here, why is that? Like this is the maximum.
Actually, you're right that if you're considering rho to be classical, it's true that the maximum above will be obtained by measurement, where you output always the x that has the highest probability, and so that would reduce to the maximum x actually of P of x. Because you would take an x to be 0 for all x, which are not the maximum, and 1 for this one.
Right.
So maybe it's true actually, it's a good way.
So what I can tell you is that we tried several ways of defining the guessing probability, and we played a lot with it. So at least at the rest of the claims of the paper, we're pretty sure about it. now the thing is, maybe we didn't define very clearly the quantities of interest. Okay, so I'll just proceed. Okay, all right. So then we also we allow for shared randomness. So our probability distribution sorry. And therefore the guessing probability is also averaged, and this epsilon lambda here okay, so lambda is some shared randomness between the parties. All right. So okay, now that we've gone through the definitions, let's look at classical correlations. How do we characterize classical correlations in such a scenario? Okay, so write the classical model for this. And there's the lambda. Okay, so this basically defines our classical correlations. So these are the marginals for Alice and Bob. Now, of course, this message, one would sum it, so it goes from 1 to D, but actually classically, So maybe I should just remind you. So X has n elements. And yeah, so the message would have the elements, and the point I want to make here is that classically one can show, and we show this in the appendix, but it's quite a boring proof, and it's kind of easy. So classically, I just want to say that we can restrict to d equals n. So classically, it doesn't help to have more labels in the message than the amount of labels which characterize your variable that you want to give. All right, so what we want to do is to upper bound the information, which amounts to bounding the guessing probability. This is just because of the definition of information. What I want to say here, this strange form, what I want to say here is that this is a linear constraint in the p lambdas, so meaning that...
If you want to upper bound the information, you mean you want to lower bound the conditional mean entropy, or the... Which I mean, you had a difference, mean entropy of H minus conditional mean entropy of H. So which one are you now binding?
So we bound information,
Okay, from above.
upper bound information, which is equivalent to upper bounding the guessing probability.
But what about the fact that there is a difference?
A difference in?
So you have H of X minus H of X knowing E, if you want to upper bound. So aren't you talking about the difference anymore? Now you talk only about the mean entropy of X?
No, it's just that this is fixed, right, for the scenario.
Okay.
So we just need to bound this, and inside this there's the guessing probability. So the only thing we need to bound information is the guessing probability. Yeah. Okay. Okay. So basically, since this condition is linear, then the classical set of correlations with information restriction of alpha is a convex polytope. Okay, and such a polytope is characterized, let me come here. Such a polytope is characterized by some facets which are linear combinations of the probability elements with coefficients R, X, Y, B, and beta, which are real. And if you have all the facets and all of these real parameters, then you have also a full characterization of your polytope. Okay. So basically, in the classical set, we find three kinds of inequalities. We find positivity. Okay. We find the definition of information in our game. So these two are always satisfied for classical or quantum sets, so they are trivial. And then we have other inequalities, and these other inequalities are the ones which can show a quantum violation, so a gap between the classical and quantum sets. Just as a note, so if I observe some correlations in nature PB of XY, the problem of knowing whether this is compatible with IX inferior to alpha is this is a linear program which we can efficiently solve, and therefore we can determine a minimal cost of information for classical correlations. All right, so yes, Pablo?
Nothing, just a quick identifier.
Sorry. You could. I have written stuff.
So you have a polytope which is evolving if you change alpha, right?
Yes, I will show you now geometrically so you can see it better. Okay. This is not the introduction anymore. Finding facets. Okay, so how do we find the facets? There are several ways to do it. I think one of the most elegant ones for this problem, at least, which is simple, is to do it in this way. So you write some conditions, you define a local hidden variable model. Let's write it like this. So these are deterministic strategies which you can easily compute. And then you require that the P of lambdas are all positive, that the P of lambdas sum to 1, and finally we give our constraint on information. Yeah, just leave it like that. And it'll just say alpha prime. Okay, so this constitutes a system of linear inequalities and equations, which we can solve by performing a combination of Gaussian elimination. Gaussian elimination basically removes the equations and removes the dependent variables. And in the end, you'll have some system of linear inequalities, which you can then reduce, so remove all the redundancies with Fourier-Motzkin elimination. So you combine these two, there's efficient algorithms to do this, yes?
Try to understand why you can decompose these deterministic strategies. So if you don't have the constraint on the guessing probability,
Yes.
Is your thing now like a bell scenario?
Yes.
You have some probability distribution, which you view as a convex combination of other ones.
Mm-hmm.
And it's always sufficient to look at the convex combination of the extreme points, which
Yes.
are deterministic strategies. But here you have the constraint on the information.
Yes.
But in the case that if I have some strategy that's a mixture, it's information, the guessing probability. Okay, yes, it will be small, it will always be smaller. The guessing probability for strategy
For the best.
for the one for the deterministic ensemble, which will use that one, right?
Yes, if you mix them, it will always be worse. Yeah.
But when you mix, you also mix what Bob is doing, not.
Yes, it's true.
You also mix what Bob is. Well,
P of B knowing XY is just a full.
no, because this is in the hypothetical game, right? It's the best thing you could ever do. So actually, the amount of information is just given by your message, what the encoding does, right? The decoding then, we just look at the scenario, we see what the decodings do. This gives us some guessing probabilities, but the maximum is defined with this hypothetical game where you.
It would be true that, okay, so if I have a mixed strategy, and now I look at let's call it purification of it. I mean, just at the convex decomposition of the deterministic one. But in general, if I consider a convex combination, I will increase the guessing probability, right? Because now you can guess, if you know how it's decomposed in deterministic strategy, you can know more, so you can better guess, right? So when you put your alpha, I mean, maybe for a given mixed strategy, the bounds out, but then if you look at convex decomposition of that strategy, you increase alpha and then send it out.
So wait, but if you have a deterministic strategy with some alpha 1 guessing probability and another one with alpha 2, you will never get bigger than alpha 1 or alpha 2 by mixing.
Okay, because if you go in your direction, like say if you start from a mixed strategy, in general, you should try to decompose it in
but that's.
increase the guessing probability.
I don't think this is the case with such a.
So you cannot do it, no?
Not with such a definition, I think.
Yes. In an extreme case, you can read perfectly x from the knowing lambda.
Okay, sure.
I mean.
Well, if all of your deterministic strategies have 1 probability, you can have 1 as the guessing probability, but not in any other case. If one of these probabilities is smaller than 1, then you'll never have 1 here. Am I understanding correctly what you mean, or?
I don't know. I mean, to me, better, no?
By mixing strategies.
No, not by mixing. The other way around. If you have a mixed strategy, you say, okay, but I know that it's actually realized in some way.
Yes.
Better, so you increase
Yes. Yes, but okay, but this is not what we do.
Because, I mean, you've written a problem right now. In general, you don't assume that the P lambda are atomistic, arbitrary. Okay? And now you want to say, okay, but without also the generality, I can consider a case where P lambda are atomistic. But is it true given bound the last equation? This is what I don't really understand.
Okay, so I don't remember exactly right now, but so the first time I tried to generate the polytopes, I defined wrongly how I was computing the guessing probability, or I was not doing the mixing right, and I had exactly the problem that you're mentioning. But I'm sure that with these definitions, this thing that you mentioned does not happen, but I cannot prove it to you right now. But I can show you later. But we did have the problem you mentioned by defining the problem incorrectly. Okay, so I don't know how much time do I have?
About 10 minutes.
10 minutes, okay. So I'll try to speed up. So all right, so let's just look at the specific scenario. So remember preparations, inputs for Bob, outputs. Let's look at 2, 1, 2. Then you just have this is the full statistics because there's no Y measurement. And therefore you just need 2 probability elements to define your probability space, which means that we can look at the polytope, which is cool. 0, 0. 1, okay, then we look here, here. Okay, so this is our initial polytope without information restriction, okay? So what does this mean? So here, you always output 0 for any x. So this means that the message that you've sent is just 0.
So it's 1/2, 1/2, or what's the value?
The probability, the guessing probability.
What is it? Your x and y?
This is, 1. Okay, so here's probability 1, but so you always output 0 for any x, right? Okay, so then the message the message content must have been just 0. So then the guessing probability associated to this is 1/2 because you're just randomly guessing. You have no information content in the message. So I'll put the 1/2 here. Here is m equals to 1, so 1/2. Here it's 0 when x equals 0, so this means m equals x. And this is m equals x plus 1, but Bob, of course, can just flip the message and get the right guessing probability. So then this now is the guessing probability. Okay, you have 1 of guessing probability here and 1 here too. Okay? And so basically you see what I will be doing. So if I want to say that the guessing probability is bounded by alpha, which is somewhere between 1/2 and 1, then just pick a point here, 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 and this defines your classical set under information restriction, and these are the facets that you get with this system of inequalities and equations. These are just positivity, and this is the information definition. So here it's completely trivial, but in other scenarios it's not anymore. So that's what I want to talk to you about now. It's a scenario where this is not trivial. Okay, maybe I think I'll have to skip a few things. Let's say, okay, just quickly present the quantum advantage. So we looked at 2, 1, 2, 2, 2, 2. There was no quantum advantage at all. And the simplest scenario we found.
What is 1 bit? What is the middle?
No, sorry. So this is number of preparations, number of measurements of Bob, and B. And the message is always classically restricted. The dimension of the message D, which is not in these parameters, is restricted to n, which is so number of x. Okay. No, that's the thing. So I mentioned before, classically we can show that you don't need more labels in your message than the number of preparation, and we can show this quite trivially just by saying that we have a finite number of deterministic strategies, therefore you can show that you don't need more labels. And we do this in the appendix, but I didn't want to prove it here because it's a bit boring. But then, okay, so the dimension of the message here is 2, 2, 3, basically, to define the classical set. So I'm not talking about quantum yet. So okay, so this is the first scenario which shows some quantum advantage. In this scenario, we have two facets. So this is a correlator, which is defined like this. Okay, and so the first facet okay, so as you can see, we can have defined these facets continuously for any value of PG within the accepted values for this scenario. So, okay, these are the two facets we find. I will not look at this one. I'll just quickly talk to you about this one. So this facet is exactly the same that is in the paper where they looked at the dimension bound. They also found the first quantum advantage here. So this is exactly the same facet. And it was found by Gallego in 2010, Rodrigo Gallego and other co-authors. I can give you the reference later. Okay, so if you take such inequality, then you can define a strategy. We have 3 inputs, 2, 2, and some lambda, and we can restrict this lambda to just be 1 bit. And the strategy, I'm wondering whether I should just give you this. I'll give you the strategy quickly. Just, I don't have much time. Okay, so if lambda equals 0, then Alice chooses one of these states. I mean, uses this ensemble. Okay, and Bob will make some measurements like this.
So it's a qubit because
it's a sorry?
so you have 3 states, but 3 so that's because the input is a trit, classical trit, right? But
Yes.
these are 3 qubits. And
Yes.
these are qubits because what? Because of the fact that the output is 2-dimensional.
No, because yes, sorry, because first I'm looking at information between 0 and 1. And of course we can go up to log 2 of 3, but this is the model for up to 1, and then the model switches. Because we don't, I'll come to it. So this is just so up to 1 bit, okay? So here is still using qubits, okay? And then the other one is just basically, so the ensemble here is 1/3 and these states, and lambda equals 1 will just send nothing, and Bob always outputs the same thing. So basically this is 0 information, this is 1, and you mix them and you can get anything in between, okay? And then basically for the strategies between 1 and log 3, we'll use the same one, which gives 1 bit, and mix it with a strategy which uses a Q-treat which just sends X, okay, which then can achieve the maximum. So these are the best, close to best quantum strategies we found. These are the most elegant ones which are close to the optimum we found, but we don't know how to find the optimum, so this is an open question. We don't know how to characterize fully the quantum correlations. Okay, so now that we've looked at the quantum violation, I want to also say that we also get some bounds which are device independent or theory independent. Okay, so basically we want to establish a general theory independent lower bound on the information. And the way that we do this is that we say we have some PB of xy, and then we allow for some post-processings of the output, meaning that so from y and b, from Bob, he can produce another output, b prime. Okay, this is in the case where the original scenario doesn't have enough outputs. Okay, so I'll just write down the thing. So this gives constraints with post-processing on the information, which right is yes. Okay, so the only thing that we do is impose information restriction, but we allow for post-processings of the outcome. And by doing this and looking at the particular scenario, so the one we were looking at, 322, we can try to see what is the value of the facet if you only make such an assumption. So basically you don't give it any underlying model, any local hidden variable model, or you don't say it's quantum mechanics. And in this case, you can also do the Gaussian elimination and Fourier elimination thing, and you obtain a curve. So now I can show you the curve, the classical quantum and device independent curve. So this is information, log 2 of 3. This is 1 bit, here is 0. The minimum value of, so I'll call F1 is the value of the facet. Minimum is 1, maximum is 5. So then the classical curve goes something like this. The quantum goes like this up to 1, okay, something like this, and then switches because we have to switch the model because we don't have the optimum, and we don't even know if it will be smooth, the optimum. And then we have some, so classical quantum, and then we have some theory independent curve, which goes like this. Okay? So these constraints that we came up with are necessary to bound information theory independent context, but most likely not sufficient. So we're not claiming this is tight at all. So basically, if you find that this linear, so you can cast this as a linear program, are the correlations compatible with such information restriction, and if you find that the problem is infeasible, then you know that you require more than alpha information to produce your correlation. So this is a device independent test on information. All right. So I have one more thing to show you, which is the thing that I mentioned about the relationship between entanglement-assisted classical communication and quantum communication, and then I will conclude. So, okay, so the two scenarios are like this. X, A, entanglements, we have some classical communication, classical message. Okay. So the protocol goes as following. Alice measures A of AX. By doing this, she collapses Bob to Yes, then Alice is allowed to send a classical message, which we can just write as a set of states which are all diagonal in the same basis. And now Bob can make a measurement BB and generate some correlations PB of XY. Okay, so the guessing probability for this since the entanglement is pre-shared, actually the information cost comes all from the message. Okay? So in order to compute a guessing probability, mu AX okay. So this is the entanglement assisted classical communication case. So let's look at the quantum communication one. So in the quantum communication case, X, A, Alice sends a quantum state to Bob, which then makes a measurement. Right, so in this scenario, Alice samples some distribution P of AX, and then she can generate a classical quantum state, something of this form, and send it to Bob. Bob can then measure this message and reproduce the same correlations as before because he's just looking at the same message. So now the whole question is, which one of these costs more information? And so we try to write the guessing probability for quantum communication case. Trace of now this is two systems which are held by Alice, classical and quantum. So this is a measurement on both. Okay. And now what we can do is, because we can bound sigma through by the identity, then we can say that this quantity is smaller or equal than trace of mu AX times NX, and this has been traced over the quantum system, so right here you see. Okay? And now you see that we have there the same expression that we have here, meaning that, where do I have some space? Meaning that the guessing probability for the quantum communication case is always smaller or equal than the entanglement assisted case. Therefore, the information cost in the entanglement assisted case is larger, okay? And which means that for the same cost of information, everything that you can do here, you cannot. So everything that you can do here, you can also do here, the quantum communication case. And this actually solves the long-standing problem that people had using the dimension bound and other methods to try to figure out the relationship between the two. Okay, it's this protocol. All right.
So you have like minus 500.
Sorry, I'm concluding now.
So you have an inequality, so you say everything you can do with an entanglement assisted protocol can be done with the result is shared entanglement. But why do you have an example? Why you don't go?
We have an example. It was an example that already existed for the dimension bound case, but now that we've shown this, we know that this example actually shows a gap between the two. But sorry.
It's too long to show.
No, it's just I have never prepared it to show it in a talk, but it would be interesting actually to look at that. Yeah, I just know about this result. It was another paper by one of the co-authors, so he knew about this result very well. So yes, but it would be interesting to look at that and even look at have a few examples of this to show. Okay, so just concluding. Okay, so basically we characterized this classical set fully. We found violations, quantum violations. We also showed device-independent bounds on information and solved the open problem on quantum communication versus entanglement-assisted classical communication. So, as just things that we would like to look at in the future is how to characterize quantum correlations. So, the quantum set under information restriction. Also, we'd like to find gaps, so between what you can do with a dimension bound and what you can do with our information bound. So this is something that I didn't talk to you about it. It was one of the things I wanted to show, but I skipped only that one because of the time. So basically, we are able to show this thing that I said in the beginning, that you can have, if you restrict the information to 1 bit, you say you want it exactly to be 1 bit, then in the 4-to-1 random access code, I hope this means something to you guys. So it's you have 4 bits, and you want to guess which of the bits Alice inputted. So for this particular game, with 1 bit of information, we show that you can do better, you can have a better score if you use a Q-quart mixed with noise than a qubit. Right? We have an explicit example of this, but the gap is very small. So in the future, we'd like to find bigger gaps between dimension and information restriction, even maybe to do experiments. And yes, and finally, also we are interested in knowing whether there is an unbounded classical to quantum advantage in some cases. We found this, but without shared randomness. We don't know if with shared randomness it holds. Yes, I think that's it. Thank you. So maybe there are a few more questions.
Postpone the question because you have the next talk in November.
Ah, sorry.
So why are you binding the information based on the mid-input bit?
Mm-hmm.
Is it because it's you consider just one single instance of all this? And why don't you consider like a regular Shannon information?
Yes, so we were interested, the initial idea or intuition, but of course this has to be made much more precise, and we just eventually found something which worked and seemed to be correct, was that we wanted to bound information in the one-shot guys. So
This
from round to round.
information, is it known to be to have properties of an information? I don't know.
Yes. This is this.
The usual measure of information is based on Shannon entropy. Right?
Yes. So Shannon entropy is in the asymptotic regime for n rounds, and we were interested in looking at the one shot, and this was we based ourselves in this Renner and Ciganovic papers. So it's papers by Renato Renner where he looks at the conditional mean entropy and relates it to guessing probability and talks about single shot information theory. So that's where we found this. And actually, one of the co-authors at some point met with Renato, and Renato said that this was the right quantity to use. Although I'm not sure exactly in which scenarios he meant and why. I think this is probably not clear. Maybe in the simplified scenarios we looked at, it is okay, but in general I don't know.
You need something linear, so most probably if you were using Shannon entropies, you would never have got such a structure with
that too.
I wonder if this definition that you used.
But then also physically you wouldn't be bounding it at each round, I think. I think that's the main subtlety about this conditional mean entropy, from what I understood.
In theory, it's a difference now because in PBXY you take one round. So then you want to claim about the information content of the system. And as you said, for this you consider a measurement that has nothing to do happening in box B.
Yes, you are
so
right.
Yeah.
Absolutely.
Experiment where you have many copies of the state, and then you also have joint measurement, and then it's more a Shannon type of entropy that would be the relevant quantity.
Absolutely. We didn't look into this into as much detail as it deserves. Yes.
I wonder if this is like the formula looks somewhat like analogous to like the standard entropy formulas or for mutual information and so forth. Is it like, can one prove that would be the mutual information between the input and an output over the optimal measurement? Like the mutual information defined normally based on mean entropy.
Yes.
Is that correct?
Yes. Actually, we in this Ciganovic and Renner paper, they say that they call it one-shot accessible information, and when it's one-shot accessible information, I think you can relate it to the mean entropy. But I read these papers a long time ago, and they're quite.
It's quite suggestive that would be choices.
Yes. But this is something I'm really looking forward to understanding better. So if anyone is interested in discussing, I'm really looking forward.
Okay, so next time you speak again.
Thank you.